very much for such an amazing gathering. I've been enjoying every single talks for the past 2 days. So very honored to be here. And today I would like to share with you this exciting direction I believe is the future, which is to use signal processing to bridge the great divide between gate-based computation and analog-based control in order to really achieve faster near-term applications. And because of this session is dedicated to learning, control, metrology, so I'll focus on its applications in quantum metrology and gate learning. And I want to start by pointing out that there's a fundamental connection between two very different approaches: the digital gate-based approach, which has extremely high modularity and programmability, but unfortunately it's not as flexible. So it's only useful in the far future of fully fault-tolerant regime, or at least for practical applications. And the analog regime, which is we use system Hamiltonian, do continuous evolution to, for example, emulate or to simulate our target system. And it's extremely flexible, and most of the Science Nature cover paper are done with the analog system. But at the lowest level, both approaches rely on pulse-level control optimization. So because of this, my team have been thinking about a new hybrid approach that allow me to use the advantage of the modular structure of a circuit without having to forsake the flexibility of a tunable system. And so we chose this framework called quantum signal processing, which I'll introduce more detail in the next slide. But on a high level, quantum signal processing framework allow us to construe computation as a signal processing process, where the input signal is the realizable unitary and output signals is the target unitary or dynamics that I want to simulate. And to be more precise, just like the conversion of an audio signal in the classical processing into an electromagnetic signal and then back to the audio signal in order to realize a telephone call. In quantum signal processing, our target input system is usually, the signal is in form of a unitary, but because when we talk about signal, we always talk about something that changed with something, right? So therefore, it's a unitary that changed with a parameterized angle. And the output has to be something measurable. So this is an example, which is the transition probability between 0 and 1 after I apply my signals. And the programmable part of the signal would be the axis of the rotation. And so if you have less programmability, for example, just one rotation, then the signal will look very simple, like a cosine function. But as soon as you have 3 programmable variables, you can choose them to produce a Mexican hat. In fact, this groundbreaking work by Ike, Ted, and Guang Hao showed that this is a universal framework to realize any n-degree polynomial simply with n different unitary in sequence. And moreover, as you can see, this is not just limited to single qubit rotation like I showed in this simplest form. It can be generalized to multi-level transformation of an embedded Hamiltonian such that I can realize any polynomial degree of function over a matrix. What is the use of that? Everything. Basically, every single algorithm can be framed as a transforming some available unitary into a polynomial transformation of that unitary. And the one most salient application is the quantum simulation, where we can use polynomial function to approximate an exponential function of a Hamiltonian. And the most remarkable thing is also that quantum signal processing-based method is today what we know the most optimal in regard to the query complexity for simulating sparse Hamiltonians. Unfortunately, it's still not NISQ-friendly, and there are 2 reasons. The first reason is all the previous methods have assumed that I will use universal gate set to decompose this QSP into, despite the fact that QSP itself have this type of hybrid analog parameterized form. So that decomposition into universal or finite gate set is extremely expensive, which results into a gigantic circuit, which therefore requires us to have extremely low gate error. A second reason is that in order to realize transformation of a really hard to realize Hamiltonian, we have to encode or embed this Hamiltonian inside a big unitary, and then perform transformation only on this upper left corner of the Hilbert space, and we throw away everything else. So that requires additional redundancy, or trash, I would say, where a lot of measurement correspond to unuseful computations. So to fully unleash the power of QSP, my team would not only not throw away this trash, we will actually analyze its full dynamics and turn it into a treasure. Moreover, we don't want to brute forcefully decompose everything into gate-based circuit. We actually want to maintain its original hybrid nature of a parameterized rotations to truly use it to do something that's useful right now. And in fact, there are a lot of things we can do right now, and we have demonstrated on real quantum computers. First of all, we have this new method to characterize quantum gate to the highest accuracy ever achieved, and for the first time achieving optimality. And secondly, we were able to generalize it to not just learning quantum gate, but learning multi-qubit Hamiltonian. But so far for second target, it's a time-independent Hamiltonian. But this is also a very challenging task because analyzing the dynamics of a many-body Hamiltonian is challenging. And as a result, it's hard to come up with simple, deterministic, and optimal learning method. And third, we generalize it further to allow time-dependent Hamiltonian learning, where we can learn pulse, control pulse level information. And so this corresponds to like the full, fall into the direction of how do we characterize, calibrate, verify our control. And we also look into ways that allow this type of new control method offered by the state-of-the-art control electronics, like feed-forward, feedback, real-time measurement-based operations into QSP, which before our work was not there. And we want to see what kind of advantage can we further extract from it. And that definitely requires us to analyze not just the useful part, but also the not previously discarded trash part of the dynamics. And lastly, we can show that with QSP, if we do take advantage of the full dynamics, we can cancel noise without additional error correction through this type of ensemble-based error mitigation. But today, I will focus on the first two topics due to time limitation. And I want to start with the most, I think, useful application, gate characterization. As we know, in a real quantum computer, for example, this is a tunable qubit in Google's device. When we want to realize the perfect CZ gate, for example, for error correction, in reality, we end up with FSIM gate, where there's unwanted swap between 0, 1, and 1, 0. And to really scale the system up, we have to reach an error that's below an error threshold in the fault-tolerant error correction that's extremely low, say 10 to the minus 4. But the problem is, in order to reach that level of accuracy, the metrology accuracy has to be even lower. So unfortunately, before our work, all the gate learning cannot even reach this level of accuracy. Meaning, even if we cross the threshold, we cannot verify that we indeed have crossed the threshold of fault tolerant. And so in order to really achieve that, we have to look at the most accurate and efficient method. So here I characterize different gate learning methods based on their efficiency and accuracy. So the lower right corner would be the most efficient and accurate. And so that's the kind of work we based on, which is the periodic calibration we developed at Google. That also allow us to learn the open system dynamics at the same time. And so the price we pay is we have to have the most detailed information of the system to really push our accuracy to the extreme limit. But that's still not enough, and I'll tell you quickly why. So for periodic calibration, the basic idea is very simple. I linearly amplify the parameter I want to learn by repeatedly apply a target gate, for example, the imperfect CZ gate, or we call it FSIM gate, K time, and measure the transition probability, for example, between 0, 1, and 1, 0, trying to learn the angles and the phase. And so obviously, the transition probability will depend on the parameters I want to learn, and I can invert or fit these functions for different depths and extract the parameters. And because, as you notice, this amplification factor K will simply amplify the parameter, so that gives us a quantum advantage of quadratic scaling in uncertainty versus the depths versus the number of amplification, which is quadratically faster than simply measuring this K times more. However, there are two major problems. One is there are drifts in some of the parameter, like the frequency of the qubit, which can introduce a phase drift in phi. But because our probability is a nonlinear function of theta and phi, this drift in phi directly prevent us from learning theta accurately. And moreover, this type of fitting-based method requires optimization. So it's not provably optimal. Sometimes the black box does not really give us the optimal solution. And another problem with this method is, although its Heisenberg limit is not optimal, meaning the scaling factor in front of this quadratic scale is not optimal at all. It's around 0.1, which means if I want to achieve the accuracy to verify the crossing of the threshold of fault-tolerant error correction, I need around 1,000 depth circuit. That is beyond any quantum computer that we have today. We're working at hundreds of depths of circuit. So we want to make it optimal. What does it mean? We want to reduce the multiplicative factor by 4 magnitudes. And so in order to do that, we have to have an optimal way to analyze, to learn the system. And moreover, we want to get rid of the black box optimizer. We want to make the learning deterministic, and so therefore provably optimal. And in fact, we can do that with quantum signal processing. And I won't have time to dive into great detail how the algorithm works. But the structure is similar to a periodic circuit, except after the measurement, I'll do nonlinear transformation on it, such that the scaling of our algorithm in a short depth limit is actually faster than Heisenberg limit. And the consequence of that is we're reducing the normal required depths for achieving the highest accuracy from 100 depth circuit to a depth 5 circuit. So this is an experiment that we did on 17 pairs of 2-qubit gates on different qubits in Google's device. And we're comparing the prior art with our method in regard to the variance of learning theta. And you can see the previous method go all over the place, and you have to take a square root of that to compare with 10 to the minus 4. So they are around 10 to the minus 2. But we are sitting very closely between 10 to the minus 3 to 10 to the minus 4, even in the real experiment, and because our method is also robust to noise. And I want to now move on to a harder task, which is learning Hamiltonians. And it's very hard because if I do have a generic Hamiltonian, say fully connected, the dynamics is just crazy. I can't afford to analyze it analytically in most cases. So the current method for learning Hamiltonian amplitude is to turn off all the couplings except one and learn one at a time. And that is not efficient at all. Moreover, it's not accurate, because what if there's crosstalk that only manifests when you turn all of Hamiltonian together? This type of contextual error is completely invisible in the current method. So we want to increase the efficiency by parallelizing the learning to allow the learning of all the amplitudes simultaneously without having to turn off any of them. And also we want to parallelize such learning. And the trick we perform here is very simple, is that if you have a Hamiltonian that allow me to find a basis transformation that's easy to implement, such that after the basis transformation, it becomes a block diagonal structure where each block is only 2 by 2. So then you probably can see how then we can directly use the method I introduced in the previous work, in that each 2 by 2, I can learn it with a similar process as the quantum signal processing phase estimation. And moreover, because they are in a direct sum structure, they do not affect each other, so we can parallelize the process. And so this is a very recent work we just put out on arXiv. And you might ask, okay, that sounds like a high standard to have this type of direct sum structure. But in fact, a lot of real Hamiltonian already obeyed this. For example, the Rydberg Hamiltonian, the ZZ type of interaction, where we can introduce a single X or Y rotation to have this type of perfect block diagonal 2 by 2. And also the XY Hamiltonian that is used in trapped ion and superconducting qubit. Of course, this is assuming that we don't have leakage, right? If we do have leakage, then it's a little bit much more complicated than this. So we have evaluated our method on the Rydberg atom system that QRA system have, and we show that indeed we can achieve this type of 1 over depth to the power of 4 scaling, which is a little bit counterintuitive. We only have a depth for a circuit, but we have 2D minus 1, many of them. And somehow our algorithm is using it as if I apply this D circuit in sequence coherently. And so that's one of the main advantage of this type of nonlinear transformation we're using with the QSP. And so we show that a depth 10 circuit suffices to achieve the highest accuracy ever shown in the experiment. So we're working with Harvard and QRA on deploying this method. And apart from that, we can also prove the optimality. Our method is inherently robust against noise, because at the same time of learning coherent angles, I can extract the depolarizing noise perfectly. And we show that the spam error does not really affect our estimation to the first order. So this is a simulation with different type of noise versus the depths. So I want to move on now to I think the most exciting cutting edge frontier of using now QSP to learn time-dependent Hamiltonian with a pulse shape. I want to learn the pulse shape. And we take inspiration that in the real device, when we want to generate a pulse, we usually start from some digital values of a piecewise constant pulse and send it through a DAC and convert it into analog signal. In that, fundamentally speaking, there's not infinite amount of degree of freedom in the pulse. And so we can use this piecewise constant nature to learn a pulse extremely efficiently. The rough idea is we will convert an analog signal through digitization, where, for example, the analog signal is realized by a time-dependent Hamiltonian with a phase phi that's changing in real time continuously, for example, produced by a DAC control. And we want to learn a shape. And the first step is we discretize it into a piecewise constant pulse. And we perform the learning, and then we convert it back. And the learning is performed by harnessing the powerful analytics of QSP, where here the learning of different phis become learning of different phase factors in QSP, which can be done analytically. I don't even need optimization. Moreover, we show that the conversion can be done perfectly without adding extra noise, so that we can show that overall there's no limitation in how accurate our method can be in learning pulse, in that as long as I have more discretization, which is L, my error will scale quadratically with L, 1 over L squared. And of course, in reality, nobody needs infinite L because your control electronics is not infinite accuracy. So we only need to match L with the required amount of accuracy. And also, this is the first method that's provably robust against both stochastic control noise. So here is an example where if the target control is a red line, but the actuated control has perturbations on top of this perfect line, we show that our method can learn perfectly this tiny stochastic noise on my control pulse. And we can also prove for the first time that this method is also optimal. And we can also generalize this to multi-qubit pulse learning. So with 4 minutes left, I want to quickly touch upon a very exciting frontier that we just get started, which is to introduce a feed-forward element to QSP to see what other advantage can we achieve. So in the conventional QSP, so this is a conventional QSP circuit in a multi-qubit regime. It's a little bit more complicated than a single qubit. You just need a bunch of unitary, its conjugate, and control knot. But the hardest part is this part, which is it's only successful if the measurement on all the ancillary qubits is 0. Otherwise, we discard the whole computation, redo. So this is very expensive. And instead of discarding everything when the measurement is not 0, this is an example of a simplest possible feed-forward QSP, which is called one-step QSP. We can generalize it to multi-step, which is based on the measurement. If it's all 0, I won't do anything. But if anything else than 0, I'll feed that information classically to trigger this single X rotation. And so such simple structure allow me to convert trash to treasure. Why? Because if I failed my all 0 heralding, I will be left with something which is the Q matrix, I don't have time to tell you, that's related to the thing I want. So if you truly analyze it, you realize all you need to do is do an X to flip it back to what you want. So that's the high-level idea of what this feed-forward can do, even with just a single step. But of course, to use it for something useful, we have to have multi-step feed-forward. So one of the problems we show that there's exponential separation is this type of band projection problem, which is if your Hamiltonian system have many energy levels, but they obey this type of band structures where different energy are clustered together but separated from each other by a band gap. And we show that our feed-forward QSP with multiple steps can help me project any arbitrary initial state into one of the energy bands exponentially faster than either stochastic QSP or the adiabatic algorithm. And the main idea is because this type of feed-forward allow me to do a binary search down this energy tree. So therefore, the number of search I need become polylogarithmic as opposed to polynomial in the number of bands. So I want to quickly conclude, which is we believe there's a way forward where we're not strictly sticking to the existing gate-based fault-tolerant, future and path roadmap, but instead we're taking advantage of both the modularity of digital side and the flexibility of analog side. And in the process of this bridging using QSP, we can find so many near-term applications in control characterization, in system learning, and in the application discovery that is very much more friendly for the near term. And under this framework, the nice thing is different type of algorithm, different type of task become unified as signal transformation. And so we can therefore go beyond what we can originally do in quantum metrology by just simply linearly amplify things, because we can do any nonlinear transformation we want. So the zoo of all the animals of metrology is just endless. We only just started to touch upon what we can do with QSP for metrology. And so these are the first sets of the example where QSP is actually useful in the near term, and it's being demonstrated on the real quantum computer. And so to look forward, I think one exciting thing to ask is what other kind of exponential speed up can we discover? For example, factoring algorithm we know cannot be mapped to a simple quantum signal processing algorithm. It needs a feed-forward element. And so if we can achieve factoring with feed-forward QSP, what other hard tasks can we solve with feed-forward type of algorithm? Especially given the advantage and the cutting-edge control electronics that's becoming available. And another, I think, very important direction is, can we integrate error correction routine inside the algorithm itself, as opposed to separate from the algorithm as a different layer? And so we have shown in the work that will be published soon that if you analyze the error dynamics inside QSP, indeed, you don't necessarily need additional error correction if the error obeys certain property. Moreover, we showed that, for example, a surface code measurement is a type of QSP. It's a type of a linear order transformation. It's the first order polynomial transformation. So if that correspondence can be extended to all type of error correction process, that would be an amazing breakthrough. So I want to thank, this is recounting, the timer just recounted, but I would like to thank my amazing collaborators. Yulong Dong, who used to work with me as a student researcher at Google, now he's a professor, incoming professor at U Michigan, and many of my students from UCSB, and my collaborator from Google, Jonathan Gross. And I'm hiring postdoc and grad students. So please reach out if you're interested in joining us in the sunny SoCal. Thank you.
Thank you, speaker. Quick question from the audience? Well, if not, I want to take this privilege maybe to ask a question of myself. Maybe I missed that part, but is there any advantage of QSP to deal with temporal dependent Hamiltonian? Or is it a problem about QSP for calibration to fight temporal drifting parameters in the Hamiltonian?
Yeah, so what's the main advantage for using QSP for learning time-dependent Hamiltonian? Is that the question? Yeah. So unfortunately, there's no good alternative to really compare to. So all the existing methods are empirical, and there's no provable performance guarantee, let alone a robustness guarantee. So I have to say this is our really first attempt to learn pulse at extreme high accuracy at whatever accuracy you want, right? This type of scaling guarantee, right? So I would love if someone tell me some other literature where I can compare to, but I think this is a really uncharted territory because for the longest time, people don't really care about characterizing the exact pulse shape, right? What you really care, so far, most people care is the unitary you implement at the end of the day, which can be optimized through AQC25 and other tomography routines. But as we progress to really use the full power of analog, we might want to do time-dependent simulation, right? We want to emulate some really intricate phase transition. And at that point, we will be sensitive to pulse level information. And so I think this is a new direction that I would love to collaborate with experimentalists, both in application and also theorists, in coming up with different variations of this method.
Thank you. Thanks, Murphy, one more time.